Chris Atherton, who's a Senior Research Engagement Officer at GÉANT, and he will tell us about how smart cables can help us understand what is happening in the beds of the oceans.
Thanks very much, Eva. Distinguished guests, ladies and gentlemen, good morning. Could I have the slides, please? Thanks. So on the 26th of December 2004, an earthquake occurred in Indonesia. A few minutes later, this scene appeared. Residents close to the shore heard a sucking sound, and the water moved further out from the shore than it's ever moved before. What happened next was the Indonesian Ocean tsunami. Sadly, over 200,000 people passed away. 1.8 million people were made homeless. Billions of dollars, or whatever currency you want to think of, that was wasted or destroyed in an instant. Now, Indonesia had a tsunami monitoring system, but it was not integrated. People would have to go out to the seismic sensors, retrieve the data manually, and then go and figure out what's just happened. It was very slow to respond. So in 2005, just after the tsunami occurred, the UN got a task force together around the Indian Ocean, and they worked on developing a tsunami system that would cover the whole area. Now, that tsunami system was made up of lots of different things. Tsunami buoys, which we've got here, seismometers on the land, GPS receivers to measure the height of the ground and the movement of the ground. Yeah. Now, the interesting thing about these tsunami buoys is that they need to be out at sea in the deep ocean. That's where they're most effective. They have a pressure sensor that's submerged at the bottom of the ocean, and then the buoy at the top acts as a communication relay to send the data back to the tsunami monitoring center. Now, just a brief bit on tsunami monitoring. From the time that the event occurs, in total, it takes about 3 to 5 minutes for the tsunami monitoring center to triage the information, to predict and simulate the progress of a potential tsunami, to classify it, and then to send the information out to people to warn them to get away from the water. And the dissemination can be in things like a klaxon or text message or something like that. So this all needs to happen very quickly. The tsunami in 2004, from the first part of the earthquake, or the first earthquake, it took 8 minutes. 8 minutes for the tsunami to hit the land. Now, the speed of the tsunami is the square root of gravity times the depth of water. So for places far out at sea, at 4,000 meters, the tsunami will move at a speed of about 198 meters a second, whereas in 1,000 meters depth of water, a tsunami travels at 713 kilometers a second. So meters per second to kilometers per second is a huge difference. So close to the shore, it travels very quickly. Therefore, you've got less time to respond to a tsunami the closer to the shore you are, or the closer to the shore the earthquake is. So we can see here a map of the travel time that the tsunami took from the point of the earthquake, which is in the dots at the top, which if I don't know how to, there we go. The dots at the top is where the earthquake occurred, and this is how long it took for the tsunami to spread out. And it didn't just affect Indonesia, it affected the whole of the Indian Ocean countries that surrounded it. So it was very quick. Now, as I mentioned before, they've now deployed a tsunami monitoring system in Indonesia. And this map shows all of the different tsunami buoys around the world. And if you notice around Indonesia now, it's all in red. That's because all of those buoys have fallen into disrepair. 22 buoys were deployed. donated by the US, Germany, and built by Indonesia themselves. And by 2017, all of them had fallen into disrepair from vandalism or other methods. It cost in the region of about $3 million per year to maintain those buoys. The whole system cost $142 million to implement. This is the monitoring center, the seismometers, the GPS receivers, the tidal gauges as well. It's a huge undertaking, but they couldn't keep the buoys in operation. Sadly, in 2018, after the buoys had fell out of disrepair, another tsunami hit. More people died. And the tsunami system itself was able to pick up the earthquake. People were warned, but they weren't able to classify the type of tsunami that was coming in because the pressure sensors from the tsunami buoys were not there to classify it. This meant that people got the wrong information. Now, this is really crucial. We need data from the deep ocean to understand our planet, not just for climate change, but to save lives as well. Now, tsunamis don't just affect Indonesia. Tsunamis can also affect Europe as well. This particular tsunami occurred in the 1700s. Now, you might think that was a very long time ago. Before the 2004 tsunami in Indonesia, the largest tsunami in that region occurred in the 1600s. Tsunamis can occur at any time, so it's a constant threat to people that live near coastlines and shores. So, we do have a big problem with trying to get information from the deep ocean to tackle these societal challenges. And it's not just tsunamis, but we've also got deep ocean temperature, which is a key factor, a key a metric that's needed in order to understand climate change. Now, you might think, oh, there's a map here, but this is the surface temperature, which is collected from space, but we can't actually see in the deep ocean what the temperature around the world is constantly and in a streamlined way. So we need more data to get a true helicopter view of what's going on our planet, to look at the long-term data sets for climate modeling, for weather forecasting, for disaster and emergency response, and also to help train AI models so that we can look in depth at the new, at many different scientific areas that have not been explored before, the so-called fourth paradigm of science. So you might think, what about dedicated infrastructure? Well, we do have dedicated infrastructure out in the world that collects some of this data, but it's expensive to install, it's expensive to maintain. Who pays for this? And who's responsible? Not just for the infrastructure itself, but the data that's generated from it. So, as I mentioned, we do have infrastructures and they are needed. They have very specific tools and instruments which can't be replicated. And there's an example here in Europe where we've got Smart Bay in Galway off the coast of Ireland, which has a range of sensors like temperature sensors and things like this, pressure sensors, tidal gauges and the likes. But the data is only collected locally from that one place. So we've only got an idea of what's going on around Ireland, or indeed around any of these dedicated infrastructures, and there are some more around the world. Now, I mentioned space before. Maybe we would like to look at the tidal height to try and see if we can measure or to detect the tsunami that occurs using spacecraft. For that, you'd need something like the reflections from the GPS and Galileo satellites, but you'd need a fleet of 1,000 low Earth orbit satellites in place to monitor the tidal height in the ocean. The only company that's got that capability at the moment is SpaceX, And if we were to develop an instrument that could detect the GPS signals being reflected off the ocean surface, we'd need SpaceX to replace their entire fleet of Starlink satellites, which would cost a lot of money. And that comes back to the question, who pays? Who's responsible? So this isn't just a theoretical issue. The UN are even looking at this. They've convened a group of scientists to research this and to try and figure out what they can do. And they thought, well, what if there's an existing infrastructure that's out in the world at the moment, that's powered, that's maintained, that's already paid for? Why don't we use fiber optic cables? So a group was set up, a task force called the Joint Task Force for Science Monitoring and Reliable Telecommunications, which the acronym is SMART Cables. This is led by a guy called Bruce Howe at the University of Hawaii, and there's many different organizations that are involved, and their idea is to, as the cables need to be replaced over time, they'll replace them with a new design that includes accelerometers, pressure sensors, and temperature sensors that are built into the actual repeater units themselves. So they'll use the electricity and the telecoms capability of submarine telecoms cables to try and figure out what's going on in the deep ocean. And just to give you an idea, a repeater is needed every 70 to 150 kilometers on a cable across the ocean. But what if there's another way? A way that doesn't require replacing the cables themselves? There are technologies out there, which I'm going to go through now, which could actually complement that smart cable technology and provide a set of data in the meantime until the cables start to be replaced, because some cable manufacturers are reticent to change the design of the cables because the cables themselves need to be in operation for 25 years. So anything that's new needs to last for 25 years, and that's a key concern for the cable manufacturers. That's why it's not been implemented yet. But there are people that are working on it. CData, I think, is an organization who've just developed this new smart cable design. Anyway, this particular technology is called a distributed acoustic sensor. It sends a laser pulse down a cable, and the reflections that the laser reflects back from the imperfections in the cable can actually be read by the interrogator unit. This allows you to effectively hear everything that's going on in the cable. Now, a DAS, the acronym for it, it can detect whales, it can detect storms, earthquakes, volcanoes, ships, many, many things. And this technology can reach for about 100 to 150 kilometers, at least up until the first junction box of a repeater, of a submarine cable system. Now, this has been deployed. I've been working with a group up in Svalbard who've been looking at this particular technology for quite a while. They did this experiment before I started talking to them, but they have a DAS in Longyearbyen, which is in Svalbard, on the Svalbard archipelago, and the cable itself runs about 200 kilometers around the island. And as you can see here, these are all earthquakes that they've been able to pick up using a distributed acoustic sensor on the cable. They've also been able to pick up storms. So with this graph here, you might be able to see the lines or the little yellow blobs. These are actually storms off the coast of Brazil. So number 2, this long one, was a storm 13,000 kilometers away. So DAS units have the capability to be able to pick up changes in pressure from very, very long distances away. And this complements satellite data, which is already in use for monitoring storms themselves. it's not just in Svalbard where this is happening. Part of the Link cable, so GÉANT's involved in the Bella program, which is linking Europe to Latin America. And we've just deployed in 2021 a brand new cable system. And on that cable, there's a small spur that goes to Madeira. And on there, we have a dedicated cable that we can deploy a DAS unit on. And our colleagues at the Portuguese Research and Education Network, FCCN, have just signed a collaboration agreement earlier this year with the cable landing station operator so that they can use this cable for scientific research for the lifetime of the cable and use the cable landing station to host a DAS unit that researchers may want to bring to do their research. We've already deployed a DAS unit as part of the implementation. And you can see here, this is actually the waves of lapping up against the shore, close to the cable landing station. This is a long-term data set that can then be used to measure tidal height over time. DAS units as well can also detect methane emissions, potentially from oil and gas fields. So there's a lot of research going on into this at the moment. Now, that's a dedicated cable that's unlit only by this DAS unit. But are dedicated cables required? So, there is another technology called stator polarization. Google first announced this, or rather, there was a research paper written in 2018 which proposed this particular type of technology using submarine cables. Google then showed that they could do this technique. What they do is they, within an optical line card, so the actual thing that makes the network work, the fiber optic telecom signal, is a digital signal processing unit that collects information called Stokes parameters about the stretch and strain of the laser light that's received at the other end. And it's used to correct the signal to actually make sure it works, that the unit's working correctly, and to correct for any errors. And at the moment, we throw that information away. We just discard it. But every time the cable's struck, it's, the Stokes parameters change. So we can actually now see if something happens, and Google were able to show this. They detected an earthquake using this technique off the coast of Chile. There's other techniques as well. Stator polarization, optical time domain reflectometry. This detects the movement of the actual repeater units themselves. And then you've got a new one which was only first published around May this year, called optical frequency domain reflectometry. This actually measures the stretch and strain of the cable within or between the repeater units themselves. So now we've got three technologies that can measure movement, pressure changes, and acceleration of the different units, all without changing the cable system itself. In fact, it's our own equipment that's used, and potentially services where you could inject the signals from polarimeters, from interferometers, and from the DAS units as alien waves. So this is like a separately lit signal into the multiplexer, which mixes all of the frequencies together. We can offer these as services now to researchers. Now, there's a group of 24 different organizations. GÉANT is one. There's 8 other NRENs involved, and we're trying to come up with a standardized design which will allow us to not only collect the data and process it nationally, but then to make that available globally to the entire research community by integrating different national and regional infrastructures together. It's called the Submerse Project, and we're still working on this at the moment. We're not just going to do this in one place, we're going to do it in 5 around the world so that we can triangulate all of the different signals that are received, and we're going to have a constant time source, or like a consistent time source, that will enable us to coordinate between all of the different centers. So, my challenge to you is, what other byproducts of our network, of our services, could we offer to researchers to actually help them do more to perform their research? Thank you very much.
Thank you, Chris. Do we have any questions from the audience?
Thank you very much. Very interesting presentation. I have some questions. First question, how many parameters do you use to detect and predict tsunami?
How many parameters? It depends. From memory, it is the tidal height, pressure, and the actual earthquake itself, so the seismic signal itself.
And how many days to predict tsunami?
Not days, seconds. They need the tsunami centers need to be able to predict the tsunami within 5 seconds, or 5 to 10 seconds. It takes 8 minutes in total for the tsunami to hit the shore, roughly speaking. The tsunami centers have 5 minutes to be able to run the simulations and classify, and then have someone check to say, yes, it needs to go out as an announcement. So they only have seconds to predict.
Thank you. We're a little bit behind of the schedule, and I hope in the coffee break you can approach Chris and ask questions if you have. Thank you. I would like to take the opportunity to one more time welcome our guest to Azerbaijan, beautiful city of Baku. I hope you are enjoying staying here. Second presentation of this panel will be presented by Anca Hienola. Anca holds a PhD in atmospheric physics and has over 23 years experience in atmospheric science and climate change research. Her expertise extends from a new particle formation, contact phenomena, and organic compounds, nucleation, to global and regional climate modeling. And actually, I like very much that sentence she put on the website. In the beginning of 2017, out of pure frustration, she got involved in activities involving open data and open access, research infrastructure activities in several projects in Europe. I believe a lot of great things just developed because of somebody got frustrated, and we would like to welcome Anca, and the floor is yours, please.
Thank you very much. Can I have the presentation, please? Can you hear me? Thank you for the introduction. Ladies and gentlemen, hello. I'm a bit of an outsider of your world, so the approach that I had for this presentation, it's a bit different. So my presentation, I guess it's completely different than what you have heard today and yesterday. So buckle up and let's get into what's the good, the bad, and the ugly in open science in climate research. Where is the... Oh, here. Where do I press? Yes. The great majority of the environmental scientists have concluded that Earth is at or near a dangerous climate tipping point. Climate change can interact with and exacerbates many other environmental and societal problems. These include air and water pollution that compound health issues, widespread or frequent droughts, diminished resources for drinking water and irrigation, extensive biodiversity loss, including species extinction. Related factors include deforestation and soil erosion, consequences of overexploitation of natural resources for human use. Documentation of all these problems and many others are of great interest for the broader climate community. Climate change can only be understood via experiments, via satellite measurements, via in situ measurements, in combination with climate models that reveal patterns and trends that enlighten our understanding on how current climate conditions have developed from the past environmental drivers in order to predict the future climate conditions. It worked. Worldwide, although regulations exist, access to information about the ecological states of global ecosystems is limited to the public and sometimes limited to the experts as well. Governments are notoriously reluctant to share data and information that might expose their own resource use and policy priorities. And when data are shared, unfortunately, it can be so that they are overall inadequate for a comprehensive understanding of the underlying processes at work. But before diving into what is wrong with this world, let's start with a little bit of optimism. I promise you it will get worse. The broad scope of climate change impacts means that successful mitigation and adaptation efforts will require an unprecedented collaboration effort that unites diverse disciplines and is also able to rapidly respond to evolving climate issues. Let's start to open access. So in order to achieve this goal, climate change research practices have to be updated. And one of the practices is removing the key research findings from behind the journal paywalls. But things are getting better. So here in this graph, you can see that the proportion of open access studies increased substantially in time for publications containing the words climate change in title, abstract, and keywords. So in 2007 we had an average of 4% of open studies, while in 2016 we reached an whopping 25%. And of course this varied by journal rank. Across all the journal ranks, open access climate change was cited more often than the closed studies. Beyond academic citation advantages, open access climate research can have a greater societal impact when studies are communicated to non-academic audiences by mainstream news and social media. And also, and this is very important, to the policymakers. I think this is one of the greatest achievements of open access in climate research. The fact that when the policymakers do not have, they're lacking institutional access to paywall journals, the open access effect may result in a greater uptake of the primary research into the policy. Now, if we are moving to the data, we must recognize and celebrate the efforts of becoming open of several very, very big institutions, programs, initiatives, whatever you want to call them, that systematically acquire consistent environmental observations. For example, NASA was among the first ones to establish a free and open policy for data. Similar values of transparency and reproducibility were shared afterwards by several other American big programs like NOAA and GEOS. I didn't change it. Oh my God, it doesn't work. Here. Sorry. So GEOS is a very, very big one, ESIP, COPDES, etc. If we move now to Europe, we have EuroGeo, very big, Copernicus, everybody heard about it, European Space Agency, and of course environmental research infrastructures. Similar to GEO, we have in Asia AOGEO and a similar initiative in Australia. These are programs that deliver a massive amount of rich and high quality data which are related to environment. I would like also to applaud the climate modeling community. And here I will mention only CMIP6, the Coupled Model Intercomparison Project, which is a project of the World Climate Research Program, which started actually in 1995. This project coordinated climate modeling experiments involving multiple international modeling teams. I think there are over 50. And their results have been open since the beginning, since 1995. Also very important is that the CMIP 6 and 5 and the previous ones, model simulations have been also regularly assessed as part of the IPCC climate assessment reports and also by various national assessments. But it is not only about the big initiatives, isn't it? It's not only about journals. Open science, it's a state of mind, and therefore we have to acclaim the people. The main work resides on the shoulders of our climate scientists as they are transitioning now from their usual routine to the new open science environment. It is a climate of change that requires complex systemic changes which involve cultural, behavioral interventions and also infrastructural solutions. Researchers now have to learn more about how to open data and licenses and metadata and etc. Universities and research institutes also often have dedicated support like data stewards that are helping them, and there is also a need for more technological and social innovation. I think they are living nowadays a very, very exciting time. And now we can start with the fun part, because until now it was boring. Did I change? Yes. So, let's say it, come on. Climate scientists should not complain about lack of data. There is an abundance of data out there. For example, here you can see the international climate data repositories. There are 38 of them, many data. For example, GEO is one of them, or the World Data Center for Climate. Let's add on top the institutional climate repositories, 101. And remember that here I didn't add the national repositories, the general purpose repositories, environmental research infrastructure repositories, nor did I add the repositories that are not actually registered to retreat.org. So, come on, why are they complaining? As you will see a bit later, when it comes to climate data, open, it's not enough. There are several conclusions that we can draw from here. And let's go through them. The number of repositories is actually a nightmare scenario. The climate scientist is a traveler through 200 or so data repositories, wasting precious time in search of proper data. The huge number of data silos, it actually limits the access for the ordinary researcher who faces data fragmentation and unequal access to quality information. High number of repositories means higher heterogeneity. I can't say this word. So each repository with its own standards or none at all. So from the researcher perspective, the lack of harmonization across data sources, it means that much valuable research data will remain underexploited. A lot of repositories there, but this doesn't mean that it's enough storage for the data. As you can see here, climate data volumes are at all-time high and are predicted to continue to rise rapidly. However, the storage does not increase at the same speed. And this is a problem that will continue in the future. Let's get back to this picture again. So where there are repositories, there is a need for them, which means that those are the places where the climate science is conducted. What we see here is that the climate conversation continues to be dominated by the voices of selected groups from wealthiest countries. This is a picture of a global scientific system that undervalues and underrepresents the perspectives of a silenced majority of historically disadvantaged groups, particularly those from Global South. Open science indeed carries with it the promise of distributing power and opportunity to define and tackle climate challenges, but it will only do so if those who are participating in the science, in this climate science, represent the diversity of society from all corners of our world. I said it before, I said it again. Too much data becomes strangely a barrier in itself. For a discipline like climate change, climate research, solely analyzing data and applying statistics without a deeper causal thinking has very little to offer to our society. Early career scientists, PhD students, postdocs, in their majority spend a tremendous amount of time just producing and analyzing climate data. This obsession with data-intensive activities actually inhibits the progress of other important frontiers in climate research, such as developing novel research ideas or developing scientific hypotheses. In other words, we are practically failing in educating young scientists how to produce research that can be groundbreaking. And if this was not enough, it can get actually even worse. It can get actually even worse. When scientists discovered a planet in our Milky Way which was made of diamonds, public fascination and admiration was assured. Who wouldn't be amazed by the idea of a bright sparkle in the night sky? Absolutely nobody questioned this finding. However, when the scientists discovered that burning fossil fuel causes climate change, the public and political response was much less favorable, with scientists being verbally assaulted and having their reputations questioned. While it is evident that open science in general democratizes climate science to some extent, at least certainly for those who can understand its content, in isolation, it's not enough, and more actions have to be taken. Because in our rush to prioritize open science, we left the world behind. Access does not equate accessibility. Despite access, the information remain inaccessible in any functional sense for the public. People cannot apply it, people don't understand it, and they cannot put it into context. The information is accessible, but the person has no access to its real value. As people are feeling shut out of this powerful, unintelligible world of science, we scientists have to pursue yet another path. State-of-the-art science communications, in a bid not to further alienate an already fearful and suspicious population. For out of fear and uncertainty, conspiracy theories are born. And when a conspiracy theory is applied to scientific results, many people may be misguided and interpret information in a very wrong way. Scientific misinformation produced as part of this wrong interpretation may have widespread and detrimental, dire effects on the entire society. Climate change is probably one of the supreme examples of proportionality bias. It is a global scale event with enormous significance, meaning that we all can die. And scientists and governments present it as a consequence of a very small, trivial, everyday thing, like the transport that we are using every day. Scientific misinformation becomes especially acute when people are in the decision-making power positions. And I will give you very fast two examples. I don't know if you know this Q&A talk show which is running in Australia. Australian Senator Malcolm Roberts asked Professor Brian Cox, everybody knows Brian Cox, yes? To show him empirical data to prove global warming. Professor Cox knew that this was coming, so he just took out a graph. And if you need to know, this is average global temperature, data provided by NASA, open data, yes? The dialogue that followed was from another planet. So the data has been corrupted, said the senator. What do you mean by corrupted? It has been manipulated. By who? By NASA. So Cox was puzzled, so was the audience, and any normal human being would be puzzled as well. It looks like having open data, it's not enough if it is in combination of scientific illiteracy. Can you guess who is the next one? Where should I start here? He likes tweeting. But now seriously, after he took the office in 2017, his administration made decision after decision after decision to slow and deprioritize climate action. It rolled back policies that helped mitigate warming, relaxed regulation on climate polluters, it made the insane decision to withdraw United States from the Paris Climate Agreement, told the Environmental Protection Agency to dismantle the Clean Power Plan, and the list can continue many, many slides. Scientists attempted to quantify the impact of Trump's rollbacks, and they estimated that these rollbacks will increase United States emissions of greenhouse gases by 1.8 gigatons cumulatively through 2035. These are people in power, and they are leading us. And the entire planet pays because of their scientific illiteracy and misunderstanding of science. No amount of self-delusion, political spin, or fake news can ultimately protect us from reality. We have a shared destiny, and we have a collective responsibility. And there exists a need to agree on what is essential to humanity, including staying healthy, live longer, and prosper. And for this, we need to trust science, because despite its limitations, scientific research remains the only tool humanity developed to solve the big problem of climate change. Thank you.
Thank you, Anca. This was interesting and a bit scary, but yeah, we can't do anything if we don't unite with the scientists. Any immediate questions? If no, then I...
That was too much for all of you?
Too much, too impactful. I suggest we take questions at the coffee break.
Sure.
Thank you.
Thank you.
And I would like to invite our last speaker of the session, Yegana Muradova. She's a research scientist at the Republican Seismic Survey Center of Azerbaijan, National Academy of Sciences, and she will tell us about seismic activity monitoring in Azerbaijan.
Hello, everyone. Thank you for having me. I'm Muradova Yegana, an engineer programmer, actually, at Republican Seismological Survey Center. And this presentation was prepared by Saida Ismayilova, who is the head of Earthquake Research Bureau, and by the system administrator, Rugia Karimova. I'm going to be speaking to you today about the software and system security in our center. Sorry. Since 2003, our center has established a very small aperture terminal-based digital seismic network, and the current configuration consists of 84 seismic stations, and the energy source for all seismic stations is provided by the batteries, which can operate autonomously throughout the day for several days. That's the structure of our seismic network. Data is coming from seismic stations via satellite to Delta Telecom, and from Delta Telecom to the Earthquake Research Bureau. Since the independence of Azerbaijan, analog seismic stations had been operating from 1993 to 2010, and from 2003, digital seismic stations had been established in our center, in our country. And from 2014, all seismic stations had been completely digitized, and this network allows us to record even weak seismic events, earthquakes. A data center uses 5.6 version of Antelope real-time system built on 8 Mac Pro for real-time processing and data analysis, and Apple computers run on Mac OS X 10 version of operating system. These are the programs we're using throughout the day. Of course, there are more than 73 programs. That's devices we are using for seismological, geophysical, geodynamic complex research. Each station has 3-component broadband seismometer, STS2 and 2.5, 3-component epicenter accelerometer, Quantera digitizer, and Marmot. These pictures from seismic stations in the regions. That's a waveform recording of strong earthquake coming from seismic stations in real time in 2012. That's magnitude was 5.7. This is a visual representation of Antelope database. Data comes to the center via satellite, as I said, and the event catalogs are created, database is created, and event catalogs are compiled. And that's the windows our employees using while they're processing time. Each user using a map, a DBlock, and waveform windows, which is associated with a database. We send earthquakes with magnitude 3 more greater than or equal to 3 to the relevant organizations. Earthquake bulletins are prepared in these forms. That's the structure of stations in Nakhchivan Autonomous Republic for data processing, real-time data processing and analyzing for Seismological Survey Center. That's the structure of Aspen system in Nakhchivan. Oh, sorry. According to the agreement with Turkey and Georgia, we exchange our waveform data with each other, and this data exchange allows us for a better assessment of seismicity in the border areas to refine the velocity model of Greater Caucasus and determine the earthquake mechanism. Our Earthquake Bureau, Earthquake Research Bureau, ensures that the Ministry of Stations, emergency stations, receives waveform data from seismic stations continuously. Local, regional, and distant earthquakes, volcanoes, landslides, and blasts are received by the Bureau, are processing throughout the day. And that's a map which is published by Earthquake Research Bureau for the earthquakes with magnitude greater than or equal to 5 from the years 427 to 2021 on a scale of 1 to 500,000. That's a map of epicenters of earthquakes in Azerbaijan and adjacent areas in 2012. Approximately 9,000 events were recorded in 9 months. 8 perceptible earthquakes occurred in Azerbaijan and adjacent areas in 2012. As can be seen from the 3D model of distributions of earthquakes according to their depths, the depths of earthquakes varies from in the land area of Azerbaijan from 2 to 54 kilometers, in Caspian Equatoria from 2 to 62 kilometers, and in regional areas mainly from 2 to 35 kilometers. That's a Lokbatan mud volcano which is erupted on 11th August, and its parameters were set. That's the waveform of Lokbatan mud volcano. During 3 months before the Lokbatan mud volcano erupted, earthquakes with magnitude less than or equal to 3 occurred around the mud volcano. That's the Lokbatan mud volcano while it's erupted. It's videotaped. After the mud volcano erupted on 12th August, an earthquake with magnitude 3.5 occurred in Caspian Sea. 22 new stations were installed in Azerbaijan territory within the framework of GÉANT project P750, and it's called Expansion of Seismic Network in Caucasus and Central Asia of Science and Technology Institute in Ukraine. And the employees of Institute of Information Technology provided support for the configuration of modems for transmission seismic data from the 22 new stations to the Earthquake Research Bureau. That's the SEISCOM seismological software, which is used for the data analysis of waveform data coming from 22 new stations and some of the user interfaces, as you can see. And that's the SAISCOM software installation process step by step. According to the within the framework of the grant project P750, it's planned to set up 2 new servers by the end of the year in our center for 22 new stations. Our database, we want to secure our database and communication systems. Because of that, for this purpose, we keep our waveform data and other research materials of other departments on a cloud server with a capacity of 15 terabyte allocated to us by the Institute of Information Technology. And also we reserve a special room for the servers and hard disks. And in that hard disk, we also archive our data, waveform data and database. Also, in addition, security of the database and system files can get access to the by administrator, only by administrator, and this special password is changed twice a year. And also accounts for the users who is processing the waveform data created for them, and this their identity is verified by special password. So as a result, it's known who added the event to this database. Yildirim service of ANAS provides employees of its organizations and institutes with a global internet connection during their visits to scientific and educational institutions of foreign countries. This service also allows scientists from foreign countries to connect to the internet without configuration during their visits to organizations and institutes of ANAS. Our center is a member of European Mediterranean Seismological Center, Incorporated Research Institution of Seismology, Observatories and Research Facilities for European Seismological Commission, and so on. And also our center cooperates with more than 30 countries in the world. Thank you for your attention.
Thank you, Yegana. Any questions from the audience? Chris.
Question?
Thank you. Thanks very much for the presentation. It's absolutely fantastic, really interesting. I really liked the mud volcano. I had no clue Azerbaijan had a mud volcano, so that's really, really great. In terms of the data that gets collected, do you discard any of the data before you then store it for long-term archiving?
Sorry, I don't understand what.
So the data that you collect from the seismic detectors,
stations.
From the stations, do you discard, do you get rid of any of the data, or do you keep everything?
We archive all of them. From 2003, we have digital waveform data on our hard disk, and from 2014, we archive them in the on-cloud cloud server.
And like with 15 terabytes of storage, you've done a hell of a lot with that. It's because I was expecting a lot more data to be used.
Yeah. For one day, it's 2 gigabyte of waveform data.
Wow. Okay. No, thanks very much.
Thank you very much.
Thank you. So I think all of the rest of the questions we'll leave for the coffee break. Thank you, everyone, for being with us today, and thank you, our presenters, for these wonderful and inspiring presentations. I hope this feeds to give some food for thoughts and for future collaborations and actions. And with this, I invite everyone to have a nice coffee breaks and good conversations. Thank you.
Gedren.